Finally. So, what we're studying today is a type of circuit element called an inductor, which has a lot of parallels to capacitors, in the sense that capacitors work on establishing a potential difference where a uniform electric field is made and has the ability to store charge and then release that. Inductors are similar in the sense that it's a coil, and that's the means by which we produce a uniform magnetic field. And they don't necessarily store charge, but they do store it. In a way, you can almost say they store current. It's not really the right thing you want to say. Really, you want to say that they store energy. In fact, for capacitors, inductors, there may be different means to do that stuff, but ultimately it comes down to the fact that they can store energy. And just like for a capacitor element, there is a capacitance that we can talk about, and it has a particular definition to it. And for inductors, we have a similar idea. To indicate an inductor, we use the capital letter L, and that is defined, this inductance is defined as a ratio of magnetic flux to current. Magnetic flux to current. And we can break this down into other kinds of pieces here, right? Magnetic flux can be specified as magnetic field times area. The magnetic field of a solenoid, we've worked out what that was. That's the mu n times I, right? And so we combine those ideas together. The i's drop out here, and we're left with a factor of mu. We got a couple factors of n here. One of the n's come from the magnetic field strength, that comes from the flux, and the other one comes from the fact that you can have multiple loops produce that magnetic flux, so that we have an n squared here because of that. The L here comes from the fact that we took the little n and we rewrote it as capital N over L, and of course we have the area factor from the flux here. Something I think is going to happen here. No? Okay. My computer is doing a little circly thing saying it was thinking. All right. It's done thinking. So, now just like capacitance, this fraction here is it's a geometric factor, really. It's how many turns you have, the area, cross-sectional area of the solenoid, and the length of it. And there's nothing else in here that involves ideas of magnetic field or current, and that was true for the capacitor. It was a purely geometric factor. And so we have two forms, just like we have two forms for capacitance. There's the definition, which is the ratio of flux to current, and then when you simplify that for something as simple as a solenoid, we get this statement here. Now, just to be clear, inductors don't necessarily need solenoids to do this, but it's easiest to keep track of all these quantities here. Just like when we did the idea of capacitance, the formula that we got, the epsilon naught was like A over D or something like that. That was a geometric expression for capacitance, but only worked for the capacitor plates. You can have any separation of charge produces a capacitance, just like any magnetic flux with a current can be spoke of as have an inductance, but you can simplify it only if you say, oh, let's do a solenoid. And we're only going to be doing solenoids here. There is a special SI unit for this. It's called the Henry, capital H for Henry, which is defined, as you see in the ratio here, it would be Weber over amps. You can simplify that a bit to Tesla meters squared. That should be a meter squared, that 2 there. Meters squared over amps. Okay, so the symbol we use for this, you see at the bottom here, that's our coil symbol that indicates that we have an inductor. Now, the inductor is not very interesting if there's a steady current going through the inductor, because that's just no different than having a straight wire. So in this example here, our current is going up and over. So by the right-handed rule, the magnetic field is going to point to the left. And if the current is steady, well, there's nothing interesting going on about this. It's when the current changes that we start to think about electromagnetic induction, Faraday's law, and all that good stuff. So steady currents have no effect on the inductor at all. In this case here, we have a current that is steadily increasing. Now, again, the way the figure is going to work here is this is increasing, the current's going up, so the magnetic field is going to be to the left here. That is the field that's caused by the current going through here. But then as you start to increase it, then Faraday's law comes into effect. You have a magnetic field that points to the left. It's attempting to increase, so there is going to be a induced current here that's trying to oppose the change in the flux. Since the initial flux is to the left and increasing, we're going to have to generate a current that has the flux go in the opposite direction to attempt to oppose the change. And so while the current, as you can see here, goes up and over here, the induced current goes backwards, again, to try to oppose the change in the flux. And what that does is it produces a potential decrease. Now, according to Faraday's law, let's go back here. Change in flux, right? What's change in flux? Change in flux is going to be equal to the EMF of that solenoid. So in this ratio here, we're going to take the time derivative of both sides of this, and we have the time derivative of, so if I move the current over here, right, so imagine we're looking at it like this. This is going to be L times I, and since we're interested in change, we're going to take the time derivative of both sides here. That gives us a time derivative with current and a time derivative with the flux. Now we know a time derivative of the flux is, that's Faraday's law, that's the EMF. And so that statement becomes this thing down here, delta V, which is the voltage that's been established across the inductor because the flux is changing, is given by minus L di dt. The minus sign is in here to indicate that the way the current changes, the potential difference as established is opposite of that. So if the current is increasing here, that's going to result in a potential. So this is basically acting in a way as like a resistive element, having a potential across this thing here. All right, so that for if we have increase in current here, it's going to try to oppose that, and this voltage difference is opposing the increase in current. Now the opposite is true if we're trying to decrease the current. So same as set up here. If we're trying to decrease the current here, well, there's going to be an induced field that will point in the same direction to try to oppose the decrease. And that creates an induced current that is in the same direction as the pre-existing current. And that's going to result in a potential gain. This becomes like a temporary battery in a way. And the current will be able to be increased through here, and there'll be a potential gain here. And again, it's given by the same equation, because here now the di dt is negative. Cancels with this negative, therefore we have a positive increase in potential. So steady currents don't do anything. But what you can think about is the steady current has like a certain amount of energy stored in the inductor. And then if you try to change the current, you can either extract out that energy or put more energy in. So in this case here, by decreasing the current, we're releasing a store of energy. And then with the opposite example, we are trying to impart more energy into there. All right, so that's the basic idea behind these work. And I can't emphasize enough that you really need to have a change in current to do this. If there's no change in current, then the inductor is just a wire. Just a standard old wire, nothing special about it. The inductors only make sense when things change. So this is going to be an important thing in the very next chapter that we're going to do, which is on AC circuits. In AC circuits, you have alternating current. That means the current is constantly changing. That means inductors are sort of always on, in a sense. They're always doing something. Okay. So this, again, this is like the analogy to the resistor. When current is going through the resistor here, it's a drop in potential given by minus IR. Here, with the current coming through here, again, the current has to be changing in some way. If it's, well, what they're kind of showing now here, if the current is increasing, then this is the setup. If it's decreasing, that's because what they're showing here is they're showing a potential drop. So if this is a potential drop, that means the current is increasing. Okay, it's decreasing, you switch the polarity here. Again, you can see that from the math here, the di dt. If it's decreasing, you make it negative. If it's increasing, you make it positive. All right. Question for you here. Letter in the chat, please. Which current is changing more rapidly? Which current is changing more rapidly? Well, I see kind of everything out there. Let's write up these equations again. The potential difference minus L di dt, right? So if we're trying to figure out where's the current changing more rapidly, we want to create a ratio of, this is a V, sorry, delta V over L. So if I do delta V over L here, that's 1. And if I do delta V over L here, that's 4. So the answer is B. It's a much larger voltage difference for a given value for the inductance. Having a much larger voltage difference here for a smaller inductance means your current is changing more rapidly. In fact, the current is changing 4 times faster than number 1. So that's what's going on here. The answer is B. Now, secondary question, follow-up here. Follow-up. What's happening with these currents? Are they increasing or are they decreasing? What do you think? They are decreasing. Thank you. The di dt is negative. Cancels with this negative. We have a positive voltage. Positive voltage because we're going up here, right? The current's directed upward. Okay, good. So the 2 Henry, the 1 Henry, that's the value of the inductance. Whoa. Value of the inductance, right? Mu naught n squared A area over L. So however these are made, that determines the value for L. But given these potential differences, the larger potential difference for the smaller inductance, that's giving you a bigger current change. All right, good stuff. Let's do a problem. What is the potential difference across a 10 millihenry? Okay, what is... Oh, that's a pretty tree outside. It's all red and stuff because of autumn. I didn't notice it till now. Pretty tree. All right, what's the potential difference across a 10 millihenry inductor if the current through the loop drops from 150 milliamps to 50 milliamps in 10 microseconds? Now, this is a di dt. However, this appears to be a linear decrease in the current, so we are safe to turn these d's into deltas and just work out what the drop in the current is, the rate at which the current drops. So that's 100 millihenries, 100 milliamps over 100 microseconds. This is a decrease, so that will be negative. We can subtract the two currents here. divided by 10 to the minus 5, which is 10 microseconds. We have a negative out front here. Obviously, you can see that the negative from the difference here, and this negative is going to cancel out. We have a 10 millihenry inductor, so 10 times 10 to the minus 3. And that's going to result in a 100 volt gain. 100 volt gain. A drop in current means the potential is increasing. All right. Pretty straightforward question. Just showing you the basics here. Let's keep moving on. Let's talk about energy, because that's sort of, I think, the good focus to have. We did that also for capacitors. Power is given by I times the voltage, right? So there's a lot of ways to express power in circuit elements, and easiest thing to do here is just say I delta V, because that's kind of a universal thing. There's special ones you can make for resistors using Ohm's law. There's a special one you can have for capacitors using the capacitor equation. They gotta have a name for that capacitor equation. That tree is so pretty out there. I can't believe it. Unbelievable. All right. And then for inductors, we have a special form of that too, minus Li di dt. So it's the voltage difference across the inductor times an extra thing for current here. This is a crazy formula though, because it has current and changing current in the same thing. So you can see what the power is going to be here. If you have a decrease in current here, the power is positive and you release an energy. But if the current is increased and then this stays negative, and you're putting energy, you're taking energy out of a system but putting it into the inductor, which you can get out later. All right, well, the definition of power is the change in energy over time. That energy is the potential energy of the inductor. And so we have this beautiful equation right here, which is real simple differential equation, nothing fancy. Separate your differentials here, integrate from 0 to I. So this is going to be the energy that is stored in the inductor as the current increases from 0 up to some value, which we'll just call I here. So if you have a steady current, okay, in the inductor, right? It's not active, but it does have stored energy in it. And the energy that's stored is given by 1/2 L I squared, which is given by the integral down here. So when nothing's changing, you can specify this as the amount of stored energy. Okay, so this is how much you can get out. If you obviously increase this, so more and so on. Okay. Now let's look. Now, back when we did the capacitor stuff, we also took a little bit of a detour just to investigate energy density. So we're going to do a similar thing like that here. This is our statement 1/2 L I squared for the potential energy of the inductor there. And we can put in the geometric expression for L here. We had that as well. It was mu naught n squared A over L, which is what we have here now. And we can rearrange a few things here. In fact, what we can do is we can group together the terms that were originally involved in the magnetic field expression. So that's a mu naught capital N over L, that was the little n, times current squared. Now we have a current squared here, we have an N squared. We need another factor of L in the bottom, so we're going to include an L up here. And we need another factor of mu naught, so we're going to divide by that and then have another factor up here. And so what we've grouped together here in the squared term is the magnetic field strength. So we can replace that here, okay, AL B squared be in the magnetic field. And then if you see AL, well, that's the cross-sectional area of the solenoid times its length. Well, that's, guess what? That's the cylinder's volume. And so we divide by that and we get a energy density. It's the energy per cubic meter. And the reason why I'm showing this to you, because it's similar to the one for capacitors, it's a very elegant equation here. It's very simple. It just involves the magnetic field strength squared, which is strange, and the mu naught constant. And what's really neat about this is that there's nothing in here, this formula, that says that we are dealing with an inductor. I mean, it just says that there's energy density as a result of there being a magnetic field. I know we derive this for inductors, but there's nothing inherent about this that says that it's an inductor. It's just basically the space that exists, has a magnetic field and therefore stores energy. And when we change that magnetic field, right, we start to extract energy out of it. And we saw that before because that was the last lecture where we saw these induced electric fields. So that's pretty wild. Pretty wild, really, though. So here's the expression for the capacitor we had before. Very similar stuff you see here. Very, very similar stuff. So, okay. So you can add these up, actually. Adding these two up will give you a overall energy density of an electromagnetic field. Pretty wild. Let's do another problem. All right, how much energy is stored in a 3 centimeter diameter, 12 centimeter long solenoid that has 200 turns of wire and carries a current of 0.8 amps? Real straightforward problem here. Let's see. To do our potential energy of the inductor, it's 1/2 Li squared. We have a current. We kind of have the inductance because we have the geometric setup of the solenoid. So that's mu naught n squared A over L. A is going to be, it's going to be a circle. So pi r squared, but you got to make sure that you change the 3 into a radius, 1.5. And make sure you use meters, okay? Don't be one of those, well, I had something nasty to say for a minute there. I won't say it, but just make the right decisions in life. 200 squared, that's the value for the number of turns. The length is 12 centimeters, so put 1.12 down there. And we put all that in there. And now this is not a lot of energy, as you can see here. 9.5 times 10 to the minus 5 joules. It's not a crazy amount of current. And this is pretty small. This probably doesn't really have a huge magnetic field anyway. We could figure out what the magnetic field is, but this is pretty tame stuff. Now, if we were interested in the energy density, this thing is rather small, so I would imagine the energy density is not that great, but it's going to be whatever the magnetic field strength is, right, squared over 2 mu naught. Well, I've got to put in what the magnetic field will be. It's mu naught Ni over L. We put our numbers into that, we get out of 1.1 joules per cubic meter, which is tiny. I mean, a cubic meter is huge, right? Cubic meter is huge, and it contains about a joule. It's not a ton of energy. Not a ton of energy, actually. Let's see here. They both store energy. Capacitors and inductors. The capacitor do so by having a separation of charge, which establishes a potential difference. For the inductor, it stores energy, and it's not necessarily a storage of current, but it's the changing current allows there to be a potential difference that can either store more energy or release more energy. So when you say based on current, yeah, I mean, it is based on current. It's based on a changing current, though. I mean, the fact that it has current means there's a set amount of energy there. And when the current changes, then it's released. Okay, just like for capacitors, right? It has a certain amount of potential difference, which relates to a certain amount of charge. Well, a certain amount of charge relates to potential difference. So, yeah. Okay. Let's see. Just keep. All right. So now, conductors by themselves, by themselves, not very exciting. With other elements, very exciting, thrilling, unbelievable. Let's look at one example of that. LC circuits. Now you saw something like this before. You saw this with RC circuits. We combined a capacitor and a resistor. And what that allowed us to do is to create the ability to discharge or charge a capacitor over a period of time. Great. Now, having an LC circuit, we have our capacitor there, and we have an inductor there. What that's going to do is this. We start off with a capacitor. Oh, by the way, me mentioning the RC circuit stuff, yeah, there was a resistor and a capacitor, and it did a certain tasks. Throwing an inductor in there actually creates an entirely different system. That's the only reason I brought the RC stuff. Okay, so now to start off with, the capacitor is charged here. There's some potential difference because of some initial charge we're calling Q naught on there. Now notice there's no battery here, so just we can kind of be under the assumption that a battery maybe charged this, and then we're switching over to the inductor. And then we're going to close the switch. And we're going to think about what will happen here. Well, what will happen is the capacitor is going to want to discharge. But as the current starts to grow here, because this is discharging, there's going to be a potential drop that will exist here. Okay, now as the charge starts to leave here, the potential difference on the capacitor will start to go down, and then on the inductor, it's going to start to go up. They're both going to be potential drops, though. Well, I mean, this one here is when you're going from, it's loop law, right? So one's opposite the other one. But the idea is that the absolute value, think about it like that, of this drops because the charge drops, but then this starts to grow because now the current is increasing through it. And so we're going to look at this in steps here. And I'll explain the analogy at the bottom here because this is analogous to an oscillating system. Okay. So anyway, capacitor is charged, current starts to flow when we close the switch. Okay. Yeah. Wait, hold on here. You know what? What happened here? Hold on. Oh, I just hit the wrong button. Okay. So as this starts to discharge, this is going to generate an increase in current. There's going to be a magnetic field that comes through here. But what's happening now is, as soon as this is done discharging, now the current's going to start to decrease. But because the current's decreasing, that creates a potential difference that's positive across the inductor. And what it's going to do, it's going to continue to push charge through, and it's going to recharge the capacitor in with the opposite orientation we had before. So now the capacitor is fully charged in the other direction, and then the same thing is going to occur. Once this gets fully charged, the current goes to zero, then this will start to discharge again. It's going to go the opposite direction now. The current's going to start to increase, and that's going to limit the amount of current that can come through here. So it's going to take some time for this to happen. But eventually, all of that gets discharged again, but then the current starts to drop, and that's going to drive more current through, and then it's going to recharge the capacitor. So the analogy they give down here is for like a spring, a block on a spring. And for the block on the spring, we have this constant transformation between kinetic energy, spring potential, right? So to start off here, we stretch out the spring that's like storing energy in the capacitor, and then we let it go. And as we let it go, it starts to fly through here, and then it reaches a maximum speed where there's all kinetic energy. Well, that's like the situation with the LC circuit here. The current's at a max, the capacitor is completely discharged, and all of the energy is now in the inductor. But then now as that starts to go down, the potential energy is going to start to increase in the spring again, for the example the block did here, and then the energy in the capacitor is going to start to increase again as well. And so it's just like the block going back and forth. Now the block's on the other side, which is like saying the capacitor has its polarity flipped. And then the spring then pushes the velocity in another direction. Its a current's going the other way. When it reaches a max current here, it's like having the max speed for the block, and then the inductor starts to recharge the capacitor. And then we go back to the original position here. So, boy, I'm not good with my mouse. My mouse button scrolling skills are lackluster, clearly. Okay, so let's look at the math behind this now. So, where is my math here? What? Where's the math? Okay, well, let me, hold on here. Things out of order. I thought I might have put things in auto. Okay, I don't do the math. Well, I'll just do it right now. It's weird. All right, so let's go back to, well, let's just go right here. All right, so what's going on here? Loop law. What does loop law have to say about this? Well, that's what the capacitor is doing, right? C Q equals C delta V, and the inductor, right, is delta V. I'll put a little C here, the capacitor, little V here for the inductor, minus L di dt. Now, the idea is that you add up these potential differences, you get 0. So if I were to do that, let's jump ahead here actually. I'll need more space. Let me bring up a whiteboard screen share. Okay, so let me do that again. Oh, now it changed color on me. Whatever. This looks a little nicer. I'm getting good at this stuff now. A little better. Okay. So loop law. Loop. The capacitor voltage, the inductor voltage, 0. So that's going to be Q over C for the capacitor. And here we have minus L. Now it's di dt, right? But that is the second derivative of Q. And if we rearrange things here, we're going to get a dq dt, and I'm going to throw in a Q over here, and LC. Now there's actually a negative sign here because this originally up here, this change in current here, we're thinking about how the current is dropping relative to this Q here. So when I actually rewrite this as dq dt to the second derivative, this actually becomes positive here, because what I'm saying here is that the current is minus dq dt. And this Q here is what the capacitor is doing. When the capacitor is dropping in charge, the current is increasing. So this becomes a plus here. That's when I make the switch from di dt to dq dt to the second derivative. So this has a negative here. Now check this out. I mean, not everybody has to have differential equations to understand what's going on here. But, I mean, when you have a formula that looks like this, and you have just some constant here, call this, I don't know what you want to call it. Well, how about you call it omega squared, because that's what it is. Huh. But anyway, if there's an x here, right? I mean, the question you ask yourself here is, what function is equal to its second derivative, right? What function is equal to its second derivative with maybe a negative sign and a constant in front? And the answer here are sines and cosines. So the solution to this is any sine or cosine. Sine or cosine works here. And that's just the nature of it. So the fact that there's this relationship, constant relationship between Q and the change in the current, well, that both involves a Q. And so I'm surprised I don't have a slide for this. Maybe I did at one point. I don't know. Anyway, the mathematics tell us here that we're dealing with an oscillatory system. So our value for Q is given as a sine or a cosine function. Now, we would go with the cosine function here for the charge because we usually start off this, right, with the capacitor fully charged. So that's going to be a cosine function. And then you can see down here that the current, which is the time derivative of that, would end up being a minus sine function, but there's another minus in there from the fact that that Q relates, the current here relates to that Q, and we end up with a sine function here. Well, let's see here. No, it doesn't work with an exponential function because you don't get the negative sign. That's the thing. If you have an exponential function, you can't have a negative in there. You don't get the negative from the exponential function unless you want to get really wild. You want to get wild, and you want to throw a imaginary number up in that exponent. So e to the ix, that actually is a solution. E to the ix is a solution to the equation, but due to Euler's formula, those are just sines and cosines. Right? Cool stuff. Cool stuff. In fact, I'm doing that later today in my 211 class. We're doing quantum mechanics today. And they're going to learn about Euler's formula because that's where all the wave functions are. They're exponentials with imaginary numbers in them. Okay. Crazy. Now, going back to that whiteboard thing I had there. Let's go back to that. Where's the whiteboard? Is it still up there? So what's the coefficient here? It's 1 over LC. Now, you might remember this, probably not, from Physics 110, but this equation shows up in a lot of systems. It shows up in any oscillatory system. And when we did the topic of oscillations in Physics 110, and you learn this in differential equations too, the coefficient in front here is the square of the angular frequency of oscillation. So that means omega is equal to, let's go back to the picture here, omega is equal to radical 1 over LC. So this is omega, this is angular frequency, which angular frequency is also determined by oscillatory frequency, 2 pi f. And so you can see here that how quickly the system oscillates is a function of the inductance and the capacitance here. So if your capacitance is rather high, the frequency is low. If the inductance is rather high, the frequency is low. It's like having a lot more mass. It's harder to change the system if there's a lot more energy involved to begin with. So, okay. So, question for you here, based on what I just showed you about omega. If the top circuit has an oscillation frequency of 1,000 hertz, the frequency of the bottom circuit would be what? So, we are looking now at a series combination of capacitors. So you got to ask yourself, well, what happens if I have a series combination of capacitors? What does that do to the equivalent capacitance? Then go from there. A lot to think about there. A lot of people saying A. Okay, let's think about it. Capacitors in series, right? Capacitors in series, you have to do the additive inverses. So that means the equivalent capacitance will be smaller. If it's smaller, that's going to drive up the frequency. Oh, I don't know, people. I'm thinking it's C, to be honest. Right? It is C. Right? Because the equivalent capacitance, right? Series capacitors, additive inverses. So the equivalent capacitance is C over 2. Yep. And then if the C goes down, that means this omega's got to go up by a factor of radical 2. Okay. That makes sense there. One thing that's really easy to mix up here is that we did resistors last, right? And series resistors add up. Their resistances add up, but not true for capacitors. So, any questions about that? Is that clear? So we have an electric oscillator made of a 0.1 microfarad capacitor. That's a big one. It's kind of big, actually. On a 1 millihertz inductor, the capacitor is initially charged with 5 volts. What is the maximum current through the inductor as the current oscillates? Okay, fantastic. So now, the relationship between these two functions here, right? If we want to determine what the current is, we take the time derivative of the charge. That's how we end up getting the sine function in here. So when we do that, if you do that, a factor of omega comes out here. And so I max is really omega times Q naught. That just comes from just executing the derivative here and realizing that the coefficient on the sine function is its maximum value, right? Because sine only varies from 1 to -1. So we have to figure out what omega is, and then we have to multiply that by the initial charge on the capacitor. Let's take care of the initial charge of the capacitor first, because that's going to be given by the capacitor equation, which is C delta V equals Q. C is 1/10 of a microfarad times the 5 volts. We get 0.5 microfarads. Sorry, microcoulombs. And then so that goes out in the front here, and then I got to multiply by radical 1 over LC, which is what omega is here. L is 1 times 10 to the minus 3, which is down here, and the capacitor is 0.1 times 10 to the minus 6. Do all that, so all that in the calculator, and we get 0.05 amps. That's the max current. You said 50 milliamps if you want to say. But in this problem here, this voltage can be used on either of the equations. Now, since we're starting off with charging the capacitor, it's best to use it for the capacitor, figure out the charge, and then go from there. So that's just, this is a simple problem, just, you know, going over the mathematics behind this stuff. Okay, excellent. Just keep going, though. All right. Now, I didn't want to leave resistors out here. I don't want resistors to feel lonely in our discussion of the really cool capacitors and inductors. So we're going to throw the resistors in here, and then next class we're going to have a big party with all of them involved. We're going to have the LRC circuit, which sounds like a burrito at Pollo Loco, but it's not a burrito; it's a circuit. So right now we're just dealing with the LR circuit. Just throw in a resistor to this. Now, what was this going to do? Well, if inductors to a large extent act as capacitors, we would imagine here that the purpose of having a resistor with an inductive element is going to have a very similar mechanism. And the fact is, it does. LR circuits and LC circuits are extremely similar in that respect. So what happens initially here is we connect the battery to our resistor and inductor, and we let it run for a very long time. Okay, so when it runs for a very long time, then there's no more increase in the current, and therefore this inductor element here is just a piece of wire. So this is just a battery and a resistor hooked up. But then what happens is we're going to close the switch here, move the switch over, and disconnect the battery from this. And then what will happen is the current will start to drop. But if the current drops, the inductor is going to wake up, basically. And it's going to slow, having the resistor here is going to slow the rate at which that current can drop. So now let's do the mathematics for this one now too. Where is my whiteboard? Let's clear this out. Okay, so for the resistor, we're going to have the potential drop across the resistor. We're going to have the potential drop across the inductor. Let's write this stuff out. This is going to be IR. That's Ohm's law, right? And we have our minus L di dt. Now this di dt, though, is referring to the current for the resistor here. So actually when I write this out, this is actually a plus here when I do that. what happens is in one of them, right, the potentials, well, if I start off with the inductor being completely charged, there's going to be a positive uh, potential across the inductor and a negative across the resistor here. But anyway, this current here this current in the inductor refers to the current going through the resistor, and so we will flip the sign on that. And if we rearrange things around, we end up getting this expression here. So that's going to be minus RLI. Okay, again, differential equation. Which function is, the question is, what function is, the time derivative of itself? That's an exponential function. The fact that the negative's here means it is a decay. So then we can go back, and that's exactly what we're looking at here. So you get this, but then we rewrite this actually as, the way we want to rewrite this is because we're writing this as an exponential decay equation. So we actually want to think about it like this. I divided by L over R. And so this thing becomes, this is the tau, that's the time constant. So it's just a matter of how we are going to rewrite that so it matches up with how decay functions look. So here, the L over R, that's where we have to write that on the bottom like that. And that's our tau. And again, the way we interpret tau here is the current's going to drop as an exponential decay according to this function here. The value for tau is our time constant, which basically tells you the rate at which things are going to decay here. So when it gets down to 1 over E, that's 37%, that's when the time is equal to the time constant. So L over R is in units of seconds, actually. And then 2 tau is down to 13, I think 3 is what, 4% or something like that. So, all right, question for you here. What is the battery current immediately after the switch is closed? We close the switch, and then immediately afterwards, A's and C's. Good to see A's and C's. Well, obviously one is correct. Now, the way this is going to work here is when the switch is closed, the current is going to want to come through here, but that means the current is going to be increasing in the inductor. It's going to have resistance, basically. It starts off at 0. And then it gradually grows. The current can't just magically come on at 2. It's got to grow to the value of, they will eventually grow to the value of 2, because when this thing is fully up and running, the inductor is just a piece of wire. So once this has been closed for a long enough period of time, we simply say, this is just wire here, and so 10 over 5 is 2 amps. So it's going to slowly build from 0 up to 2. Okay, how is it going to build there? Well, it's dictated by this decay function with that time constant. So I'll tell how long this is going to take. What is the battery current immediately after the switch has been closed for a very long time? The answer here is C. Again, I just explicitly explained earlier that this inductor just becomes a wire once the current is steady. Excellent. All right, one last problem here. We want to know what is the current out of the battery immediately after the switch is closed. What is the current out of the battery after the switch has been closed for a long time? Okay, so we're actually going to do a problem with this. So let's see what's going on here. With the switch open, the battery is disconnected. So nothing is happening here. Okay. As soon as the switch is closed, the current out of the battery is going to be just through the middle branch here. You're not going to have anything going through the right at first because the inductor is initially going to resist the change. There's nothing resisting that change in the middle branch here, so current can go through there, and it's almost like the right-hand side of the circuit just doesn't exist initially. That means immediately after the switch is closed. And so once that happens, then you just have a 5 amp current going through the 20 ohm resistor. But as you let time go on, the current is going to start to grow in the right branch, and it grows until it reaches a max value where the inductor is basically not an inductor anymore. It's just going to be a wire. And so that means your circuit now looks like a 10-volt battery hooked up to two resistors in parallel. So having two resistors in parallel, you do the additive inverses of those. The equivalent resistance of that combo is 10. So 10 over 10 is 1 amp. So and then obviously what happens is this, that's what's coming out of the battery, and then it splits half and half on either sides here once it gets to the junction. So yeah, on the right-hand side, it starts off at 0, and it gradually increases until it gets to 0.5. Gradually increases, it gets to 0.5. Okay. Sounds good. So like I mentioned, this becomes a little bit more interesting when we get into AC circuits. Our next two lectures are going to be the basics of AC circuits. We'll introduce what an AC circuit is, and then we go through all the elements. How do resistors behave? How do capacitors behave? How do inductors behave? And then we start mixing and matching them together. And then at the very end of it, we're going to have a big party with the LRC burrito circuit thing. And then we get some really interesting systems. Then that stuff's neat, because then you're really going to start to see some real solid application stuff. Because this is all, we're going through the basics here, the basic idea of these circuit elements. But when you start building the stuff in combinations in AC, then you really start to see the beauty of the stuff, and you start to see some of the jobs that these things can do. And that's neat, and it's hinted at a bit there.